Hey everyone. So let's wait for the slide. Perfect. Okay, I just want to start by saying thanks to the organizer. Like this week is really cool, and it's my first time in Serbia, so thanks for all of this organization. But today I want to talk about fuzzing, and I want to do an introduction to fuzzing. Before we start, how many of you have used a fuzzer in their life? Oh, okay, so more than usual, which is pretty good. Okay, first thing first, who am I? My name is Josselin Feist. I'm the engineering director of the blockchain team at Trail of Bits. If you don't know us, we are a security company where we specialize in high-end security technology. We work on blockchain, but we also work on traditional application security, cryptography, machine learning, and so on. One thing that I think differs us from a lot of our competitors is that we are research-oriented, and as a result, we publish a lot of academic paper, blog posts, and also tools. And we have published a lot of open source tools such as Slither, Echidna, Medusa, Caracal, and so on that you might know. But today we are going to focus on fuzzing, and we are going to see why we are using fuzzing, what it is, how to use it, and how you can kind of use this type of technique on your day-to-day activity as a developer or security researcher. The question we are going to try to answer here, and the things we are going to focus, is how to find bugs. So if you have like this piece of code, okay, it's working. If you have this piece of code, it's like 10 lines of code, you have two functions. It's a function to buy some token based on some price, and you have a 1 to 10 ratio. When you send 1 Ether, you receive 10 tokens. How do you know if there is a bug? How do you know like, if there is something going wrong here? There is not a lot of code, but it can have some impact. Usually, you have 4 techniques to find bugs as a developer or a security researcher. The first one, the first technique, which is I'm hoping used by everyone and everyone is aware of it, is unit test. Basically, you call the function with a specific input and you try to see what's the outcome of this. This is really kind of well known in traditional software development and also in blockchain with toolkits like Ardart or Foundry. The thing is that from experience, unit tests are not going to prevent having vulnerability in your code base. And the reason for that is that most of the case when you are going to write unit tests, you are going to test for the happy path. You are going to test the program to see if it behaves the way it's supposed to behave in kind of like the expected path. The thing is that most of the vulnerability are going to lie in the edge case, in the kind of small detail or in the situation where you did not think about the code base. We actually have done a couple of research on that, and we were looking to see if there is any correlation between the quality of unit tests and the likelihood to have critical bugs in a code base based on our security review. And we could not find a strong correlation between both, which means from our empirical experience, there is no direct correlation between quality of unit tests and likelihood of having bugs. Let's say you have other techniques that you can use. The second one is manual analysis. Basically, you go line by line, you read the code. When you go to a security provider, when you go to a bug contest or a bug bounty, most of the people are going to do that. They are going to sit in front of their screen and just look at the different line of code and try to manually understand what can happen. It's really powerful, but it's time-consuming, it's expensive, and every time you change the code, you might impact what you are building. So it's not something that is necessarily robust over time. Then there are 2 categories that I'm going to do a bit more of a deep dive, which relies on tool, fully automated analysis and semi-automated analysis. By fully automated analysis, I mean tool and technique that are kind of one-click button. Something where you just run a tool, it gives some result, you triage the result, you know if there is a bug or not. A common example is Slither, which is our static analyzer. You can see on the screen our GitHub integration, where you can run Slither. It's going to look for common vulnerability, reentrancy, lack of access control, this type of things, and it's going to try to find common bugs. It's really good at finding common pattern. However, it's not going to find more complex vulnerabilities. It's not going to find things that are a bit more related to your own business logic. In addition to that, it might create false alarms. So it's not because this type of tools and technique find a bug that there is a bug, you need to triage. That say, from our experience, triaging this type of result will take you like half of an hour, 1 hour, so it's something we definitely recommend to do. The next technique, and the one we are going to focus today, is the category of semi-automated analysis. So here you are also going to use a tool, but instead of being a click button, one-click button, something you just run and you don't have any configuration or anything to do, you need to provide some information. You need to provide some configuration. It does require what we call human in the loop. So you need a bit more expertise to use. And in particular, we are going to focus on one technique, which is called property-based testing, with a fuzzer which we have built, which is called Echidna. So I've been mentioning fuzzing a bit. I've been mentioning property-based testing. What does it mean? On a really, really high level, fuzzing is just a technique to generate input to your program. If you want to think of the most basic way of doing fuzzing, from a user perspective, you open your application and you go crazy on your keyboard and you look what's going to happen to your application. Is it going to crash? Is it going to reach something which is a bit weird? Is it going to trigger a path that you did not consider? So it's really a technique. You generate more or less randomly inputs to your program. It's a technique, and it's a type of tool that is really well established in traditional security and traditional software engineering with fuzzer like AFL, libfuzzer, gofuzz, and so on. Now, property-based testing is a specific variant of fuzzing where traditionally fuzzing is applied to find memory corruption, like segmentation fault, buffer overflow if you have worked with more traditional language. Here, what we are trying to look on smart contract, we are trying to look for business logic issue. We are trying to find problem in kind of like the specification of the code base, trying to find problems that are related to the specific logic of the contract, of the code base. How we do that? First, we define properties. We define invariants. Then we use a fuzzer to generate random input to the contract, and we use a tool to check if the property or the invariant is still true no matter of the input. The way you can think about that is that on a really high level, when you do a unit test, you call a function with an input 10. You do the same with fuzzer, but instead of calling the function with 10, the fuzzer is going to call the function with arbitrary value, 10, 20, 1 million, 100. So it's kind of a way to do unit testing, but on steroid. Like you try the same kind of philosophy, but you do it with way more input. I've been talking about invariants. I've been talking about property. I'm using the same. I'm using both terms, but it's the same terminology. Basically, an invariant or a property is something that should remain true over your code base. For example, if you have an ERC20 token and you have a total supply of 1 million, one invariant is that no user should have more than 1 million, right? If you have a total supply of 1 million and a user has 2 million tokens, probably something is wrong, right? So this is an example of simple invariant you can define over your code base. Okay. Echidna. So Echidna is our open source and free smart contract fuzzer. We have been working on it for probably 5 to 6 years now. It's a fuzzer that we have been heavily used in most of our audits and also by some of our clients. You can see a couple of. Oh, can you still see it? Okay, sorry. Yeah, so it's. It has been used also by many clients directly on their code base. You can see a couple of names here. Thank you. How does it work? On a high level, you have your smart contract code, you define your invariant in Solidity, and you just run the fuzzer, and the fuzzer Echidna is going to try to break this invariant. If we take, as an example, an ERC20 token, again, a really simple contract, but here we have someone who are trying to kind of optimize gas, and they are using uncheck operation for arithmetic. If you have a bit of experience with Solidity, you can directly spot that here there is a bug. You are using uncheck arithmetic operation to update the balance, which means that there is no check, and if you transfer an amount of token which is greater than your balance, there's going to be an underflow, and it's probably going to be bad. Here, how can you define an invariant? So here, an invariant will simply be that the user, so balance, you see it? Yeah. The balance of the user is below the total supply, which you define to be 10,000. So you define the total supply of the contract to be 10,000. You write an invariant, which is 3 lines of code, and you run the fuzzer. If you run the fuzzer on this invariant, is going to tell you it failed. So it did find a way to break this invariant by calling the contract. Under the hood, the fuzzer is going to call all the functions of the contract with arbitrary value and is going to try to see if this invariant, total supply of the balance, user balance is below the total supply, is still true. Here it says he managed to find one by calling the transfer function where the destination is 0 and sending 10,093 tokens. If we go back on the example, this is a vulnerability I was hinting. There is an underflow in this contract, so if you transfer more assets that you have in your balance, you can actually do that and you receive more tokens than expected. The thing which is interesting here is that we were defining an invariant over the total supply, over the balance, but we were not thinking about the transfer function. We were just defining a general invariant of the protocol, and the further, by exploring randomly all the function, by exploring randomly all the kind of possibility of the contract, did find a bug in a place we were not looking for. And this is really, I think as an intuition, it's a really good way to find bugs, because you are not going to look at the functions themselves, you just define invariant, and the further does the job for you. Now the question that you might ask is how you define invariant, because like the ERC20 was a bit of a simple one, and how we can do it for more complex protocol, how we can do it for things that are a bit more difficult to understand. Here there is no magic solution. The way we approach defining invariant and property with our client and in the code base we are reviewing is that we have an iterative approach. We start small, we start simple, and we go more and more complex over time. If the first invariant that you are writing leads to a bug, most likely there is something really wrong in the way you are developing software. So start simple. Don't try to write Solidity invariant from the scratch. Start with English. You can open a Markdown file, you can open a text file, you can write on a whiteboard, whatever works for you, and start to think about what are the properties of your code base, what are the specifications, what should be the different behavior of your contract, and iterate. So you start with English specification, you write the Solidity code, you run the further, either it passes, and then you can start and go back on the English definition, or it breaks, and if it breaks, either you found a bug, which is great, or your invariant was false. And from practices, when you start writing invariants, it is likely that some of the invariants that you are going to write are actually not correct. You might have assumption about the behavior of your program, but this might be false. To give you kind of a couple of traditional example of invariant to give you some insight. If you have an arithmetic library, if you have a math library, you can use some of the common properties that you have seen, when you were kind of learning about arithmetic, I guess. Commutative, identity, inverse. Now, if we think about a bit more complex system, we have the ERC20 total supply example that I used at the beginning. The balance of a user should not be greater than the total supply, pretty straightforward. If we go a bit more deeper, and if we think about the transfer function, and if we think what's the behavior of a transfer. So if I'm sending 10 tokens to someone else, and I think about what's going to impact the balance, my balance should decrease by the amount, and the receiver should increase by the amount, right? I'm sending 10 tokens, I have 10 tokens less, he has 10 tokens more. Well, if you write this as an invariant and you run the further, it's actually going to tell you that it's wrong. And the reason for that is that there is a specific edge case. If the destination is yourself, the balance doesn't move. Like the balance doesn't change. If I send 10 tokens to myself, the balance is the same. So this example is just to highlight that sometimes you are going to think about an invariant in a way that it seems straightforward. It seems like, okay, you understand how the system is behaving, but actually it can be more tricky. That's why like an iterative approach, starting small and simple and moving into complexity over time is what we use. Something to consider also is to consider reverting, return false, to consider that when the function is not supposed to be able to be executed, it's not actually executed. Like for example, if you don't have enough funds, the transfer should revert or return false, depending on your behavior. On a high level, we usually categorize invariant into two categories. The first one are function level invariant. So think of invariant where you just define with respect to like a specific function. Arithmetic associativity or like the transfer are function level invariant. Most of the time, they are stateless in the sense that they don't require to change the state. I'm saying most of the time because sometimes you have a function and you need to consider the state. They are usually a bit more simple to test, and they are simpler to start with. Then we have system-level invariants. So system-level invariants are really invariants that are not dependent of a specific function and should remain true across like the entire system. The total supply versus balance of the user is an example of system-level invariants. They are more powerful, but also more tricky to define. So start with function-level invariants. Here, a kind of a simple strategy is that you just inherit from the target, you create a wrapper around the function you want to call, and you just check whatever property you want to check. So in this example, we just we check that A plus B is equal to B plus A, and we use an assertion for that. For system-level invariant, as I mentioned, it's a bit more complex. Usually, you need to set up like the system. You might need to deploy multiple contract. You might need to kind of set some parameter. You might want to get to a point where you fuzz or you have invariance into a specific state of your system. If you think about a lending protocol, you might either want to have system invariants that are going to target opening a position, closing a position, liquidating a position. Maybe you want to narrow it down and you want to say, okay, I'm going to have a concrete example where I open a position and I'm just going to fuzz what can happen after a position is open. This is depending on what invariant you want to test. This is depending on the complexity of the system. If we go back on this example, so again, there is two functions here, buy, which is just a stateful function, receive some token, receive some ether means some token. And valid by, which is going to check that you are sending enough token. And again, here we have like a conversion of 1 to 10. 1 ether is equal to 10 token. Where to start? Here we have two functions. And if we go back to our discussion, where to start, we have a stateful function, by, and we have a stateless function, valid by. So let's start with valid by. It's a simple function. You just take some parameter and revert when you don't provide enough amount. So what invariant we can think of here? The most simple, I think one of the most simple invariant we can think of, this is a function that takes some amount of token and take how much ether you send. One thing you can say is that if the amount of ether you send is 0, you should not be able to receive token. If I'm sending 0 ether, I should not be able to mint any token. So here is how you can define the invariance with a caveat, because I updated the slide yesterday, there is a bit of a typo. Here it should be assert desired amount is equal 0. This is why you don't update the slide the day before the presentation. But yeah, basically the idea is that you call the function and you check that the invariant, so you cannot, like if you send 0 token, if you send 0 ether, it should be 0 token. If you run this with echidna, it's going to say it did manage to find a bug, it did manage to find a way to break this invariance. Why is that? If we go back to the code and we look a bit more deeper, the way we do the arithmetic here is that we take the number of token, divide by 10, and multiply by decimal. And the fuzzer told us that it did manage to mint some token for free with an amount of 1. Here, because you have a division by 10, if you try to mint any number of tokens between 1 to 9, up to 10, the division is going to run toward 0, and basically, like this was the equation, is going to be 0. This is an example where, due to the lack of precision of integral arithmetic, you can basically get any token for free if you mint between 1 to 9. This is again an interesting example in the sense that we were not necessarily looking at the formula. Like the formula here is simple, but you can imagine more complex formula in DeFi. We were not looking at the formula. We were looking at the output of the formula, and by defining an invariant over the output of the formula, the fuzzer found a bug in the arithmetic themselves. Okay. So Echidna is not the only tool that works that way and can find bugs based on invariants. There are many other further out there, from DApp, Brownie, Foundry. I believe Foundry is right now probably the one which is the most used by developer. All these additional further, I think they are probably easier to use. Like if it's the first time you are writing an invariant, if it's the first time you are using a further, probably it makes sense to start with a Foundry one just because it's going to be simpler. That said, they do require a specific compilation framework. Foundry, you need Foundry. And if, for example, if you use RDAT, you might have trouble with that. And they are also, from our experience, they are not as advanced as Echidna. As I mentioned, we have been working on Echidna for 5 to 6 years now. A lot of kind of like the optimization and like the fine-tuning on the value generation, on all that stuff, have been really kind of pushed toward our usage and pushed thanks to all the code review we have done. There is an additional category of techniques and tools that you can use to check invariant. And these techniques are based on formal method. A fuzzer is just going to randomly generate input over your program and try like some of the path. A formal method-based tool is going to, on a high level, create a mathematical representation of your code and of your invariant, and is going to try to check if this mathematical representation is valid or not. They are powerful in the sense that you can have a proof. Like it's a mathematical representation, you can have a proof of what you do. That's from experience, and I've been working on symbolic execution and on fuzzer for a couple of years. They are significantly more difficult to use. There is a lot of HK, there is a lot of inside knowledge that you need to know about how this tool and techniques works, such as if you want to apply formal method on your code base, it is going to require a lot of time. While with a fuzzer, within a day, you will be able to start. So formal methods are good tools like KVM, Certora, and from one-time verification and from Certora. They are good, but we would not recommend to start with that if you are thinking about invariants. In comparison, like you can start much more easier and faster with a fuzzer. A couple of additional things that I did not mention here, but we have a lot of additional options, a lot of additional features with Echidna. We have, for example, a mode where we can target high consumption gas transaction. If you want to know if there is some risk of denial of services, we can do differential fuzzing, we can work with any compilation framework, and so on and so on. And yeah, it's free and open source. You might have heard of Medusa. So Medusa is our second smart contract fuzzer. TLDR, we are taking all the lessons learned that we have acquired by building Echidna, and we are rewriting our fuzzer in Go. It's still experimental, it's still not up to, it's still a bit behind Echidna in some of the features, but in a couple of months, we will be able to do the switch. If you like to try beta version, if you like to try experimental software, please try it and give us feedback. We are trying to make it as usable and as performant as we can. Okay, so I hope that the kind of TLDR of what you can take from this presentation is that thinking about invariant is a really powerful way to find vulnerability and to build better software. From our experience, it's not necessarily about even using a fuzzer or even using formal method, but just thinking about invariant. Go over like a markdown file, whiteboard, or what you want to use, and defining what the system is supposed to do is going to help you. You might directly find bugs just because you are writing the specification. Our clients that have a specification, that have some form of invariant or pseudo specification, they have more mature software, they have more mature code base, and you can see directly from the quality of their code when they have this type of approach, when they follow this paradigm. If you want to start, keep in mind, start simple. Start with the most common invariant, start with function level invariant, and iterate over time. Iterate over complexity, iterate over size. Finally, as I mentioned, we have been using fuzzer for like a really long time, and we recently launched a services which is called Invariant Development as a Services, where we help our customer understanding what are the invariants of the system, how to integrate with fuzzer in their CI, how to integrate like a fuzzer in their development process, how to deploy the fuzzer in the cloud, and so on. If you are interested to learn about these services, there's a QR code for that. Thank you for your attention, and if you have any question, now is the time.
Yeah.
Thanks for the presentation. I just wondering about one topic that had just come out from the Twitter recently. Have you ever heard about GPU-based fuzzing and how you can accelerate fuzzing capabilities using like GPUs like H100 or something?
That's a really good question. I don't have yet a clear answer on the GPU-based fuzzer because I haven't seen practice some of the challenge from GPU-based fuzzing solved in practice. Typically, I'm thinking about storage. Like, how do you manage storage when you fuzz over the GPU? Maybe there are some techniques that some of this team have, find a solution for. There is some, discussion over Twitter. I'm waiting to see the final result to get an opinion. But it is an interesting topic. And actually, at Trail of Bits, a couple of years ago, we were exploring GPU fuzzing, but for traditional application, not for smart contract. So maybe we will see a speed up, but TBD.
Does that answer your question? Do we have any more questions? Yes.
What has been the best case scenario for a client providing information to help make the creation of the invariants easy? I know specification also implies better code, but is a specification best, and if so, in what format?
Okay, that's a really good question. I don't think there is a specific format. We can adapt to whatever they provide. But I think if they have some form of specification or pseudo specification, doesn't need to be like fully formal. It helps us a lot, and also to demonstrate what's the status of each one. Because sometimes you have they know about 20 invariants, they have checked 3 of them manually, they have checked 1 of them with formal method, 2 of them with fuzzing. It gives us some insight into what they have done. Something that's also useful for us is to know what they want to cover, but they could not. Because sometimes, they're going to focus on writing invariant for a math library. It's a common theme, but maybe they did not consider the integration with other protocol or things like that. So it's really about understanding what they want, what they are at, and where we can get them for the next step.
Yes,
yeah, I have 2 questions about one thing. First, about when should you think people need to do fuzzing? Should they cover everything or just very specific code that had a lot of complex math? It's a person.
That's a really good question. For the invariant definition, as soon as possible. From the invariant standpoint, defining what function should be done as soon as possible. Using the fuzzer might depend on how you build the software. I think, for example, if you are writing an arithmetic library, you should probably use a fuzzer from the beginning because it's going to help you to understand better how it works. If you want to fuzz more complex integration, you probably want to start with unit test. You want at least to have a unit test, being able to test whatever process or whatever behavior of the system, and then you can move into fuzzing. But I think for anything which is standalone in that sense, like a library or something like that, you can probably start with fuzzing. For something that is a bit more complex, start with unit test and then move toward fuzzing. For the invariant definition, I think as soon as possible.
Thank you. And the second question about, you mentioned also formal verification. Of course, it's quite hard and complex thing, but can you just find the boundaries when you can just limit with the fuzzing and when you can go to the formal verification?
That's a good question. So when to switch from fuzzing to formal verification? The first question, I think, to answer for yourself is resource. How much effort and how much time you can spend into that area? Because at the end of the day, security is a budget question. How much effort are you going to invest there? If you have unlimited budget, then you can probably do fuzzing and formal verification on a large part of the code base. Then if you have limited budget and let's say you want to spend 1 month internally doing some formal method over, over your code. If you haven't started with fuzzing, it's probably going to be way more costly for you to get anywhere. So start with fuzzing. Once you have a good definition of the fuzzer and you want to apply formal method, identify the components that are going to be the most amendable for formal method and that are going to have the highest impact with respect to your code base. For example, if you want to apply formal methods on composability, it's probably going to be tricky because you might need to write a mock of like whatever contract you are interacting with. You might need to write like additional wrapper. You might need to write some stuff with respect to the underlying formal methods tool you are using. So this might not be easier for you, and you might anyway work on a model and not on the actual representation of the code. So here instead, you might want to focus on arithmetic, access control, all these type of things. Some place where it makes also sense is that if you are trying to write an optimized version of a code base, you write like your code in assembly, like let's say you go full assembly on your contract, maybe write a version in Solidity, do differential fuzzing to compare both implementation. If it passes, use formal method to do like an equivalence check over the two model. So like this is a good example where it makes sense.
Unfortunately, we don't
It's okay.
have time.
I'll ask after the talk.
Yes, feel free to chat after the talk.
Thank you.
And please give one round of applause